Hello everyone, and thanks for showing interest in my talk on digital analysis. My name is Johannes Hentschel and I am a PhD candidate at the École Polytechnique Fédérale de Lausanne, EPFL, or in German, Eidgenössische Technische Hochschule Lausanne. I am preparing my thesis at the DCML, that is the Digital and Cognitive Musicology Lab, supervised by Professor Martin Rohrmeier. The DCML is a transdisciplinary group of music researchers, and the main focus of our lab lies on the design and evaluation of computational models of music. My own research is kindly funded by the Swiss National Science Fund through a project called Distant Listening, the Development of Harmony over 3 Centuries. In this project, together with my colleagues Fabian Moss and Andrew MacLeod, we use a large collection, a corpus, of annotated digital scores to measure empirical differences between different tonal languages. Although I am speaking to you as a corpus researcher, today I want to talk less about corpus research and instead a bit more about one of its prerequisites, namely digital analysis, or what it can mean to move the analytical process to the digital realm. Of course, analysis is a really big word, so I will first have to explain what exactly I mean by it and how I relate it to this conference's topic, Musik verstehen. I will do so by taking a computational stance and by claiming that a piece of music is a high-dimensional object and that analysis can be viewed as a process of dimensionality reduction. Then I briefly share my reflections on annotations and which role they can play in the analytical process. And in the second part of my talk, I will share some insights into what changes in the annotation process when we do it on the computer rather than on paper. This presentation is part of section 3 of this conference entitled Analyse und Werkverständnis. So let us shortly dwell on the question what it means to understand or to comprehend a piece of music. Since this is a meeting of music theorists, I can be certain that this virtual room is full of professional music comprehenders. So I would like to ask all of you to quickly think of a piece of music that you comprehend, a piece that you understand very well. Got one? Okay, could you all do me a favor? Please do an introspection into this thing which is your comprehension, your understanding of this piece of music. I give you 20 seconds to simply contemplate what your personal comprehension is made of and what senses are involved. Thank you very much. I was actually trying to read your minds, but it didn't work because this video was made in the past. But nevertheless, let me try to find the broadest possible characterization of all those mental objects that have just been contemplated. First, we might say that these mental objects are deeply embodied, in the sense that they are shaped by personal experiences we link to a piece and which leave their traces on our understanding of it. These experiences include sensory perception, which leads to auditory or visual impressions and memories. Emotions, be it those from hearing, singing or playing the piece, or those that the music is thought to express, or nostalgia for the time when the piece was created, or maybe just the general feel of the piece, and so on. Many of the pieces that we understand well, we have performed ourselves. And thinking of such a piece often makes us relive the experience as a performer. Maybe we have appropriated a piece in a very creative or playful way, or it simply evokes certain characters or scenes in us. Many of us, of course, like looking at a piece through the lens of what we know about it. And I think this characterization could go on for long. Personally, I like to think of a person's understanding of a piece of music as a multidimensional, unfathomable sculpture. A sculpture that only this person alone can navigate, relive, reshape, analyze, and which is a unique result of this person's prior experiences and appropriation of the piece. To say it in computational terms, a piece of music is a high-dimensional phenomenon, and so are its physical and mental representations. Humans, of course, are not very good at imagining anything with more than 3 dimensions. If you want a very humbling experience in this regard, you can watch the video about quaternions by the great math popularizer 3 Blue 1 Brown. Let me give you some examples what we humans are very good at dealing with. A map, a diagram, a graph. Anything with 2 dimensions. 2 dimensions are just fine. Wouldn't it be great if we could just project the accomplished sculpture in our mind onto a large sheet of paper to show it to everyone? In computer science, the projection of a high-dimensional object into a low-dimensional space is called dimensionality reduction. And I would like to present you with a computational view on music analysis as a very human form of dimensionality reduction. First, let me clarify my terminology. When we ask students to hand in a written analysis of a piece, quite often the task includes analysis, synthesis, and interpretation. To avoid confusion, let's call this 3-step the analytical process. Today I want to present you with a perspective on the analytical process where the dimensionality reduction of a musical entity is performed in 2 steps, analysis and synthesis. Whereas interpretation is the opposite process, which I'm not going to talk about today. So from here on, when I speak of analysis, I mean the first of 2 steps that result in some reduced version of the analyzed object, which is much easier to digest. How do we go at the dimensionality reduction of a high-dimensional entity, such as a recording, a live performance, or an embodied mental sculpture? First, it is good practice to set a goal, to decide on one particular aspect that we want to get a better grasp of. For example, the phrase structure or some sort of motivic development. Or, to stay with the image of a mental sculpture, we want to carve out some substructure, some high-dimensional slice that can be projected and reduced to a sheet of paper without distorting it too much. In other words, the projection should remain as truthful as possible to the high-dimensional slice it represents and retain a maximum of its properties. And the way we can do this is to take the substructure, identify parts that can be referred to, represent them by some symbol, and to then arrange these symbols in a way that their arrangement represents the relations between them. The outcome is typically called a symbolic representation. When we put on our computational glasses, we can call the parts objects, and the symbols we use to represent them references. In that sense, analysis is an operation that assembles objects from a given entity and collects their references. But for this operation, we need a set of criteria that serve to identify the parts. At the same time, this set of criteria defines the object's property values or features, and maybe a type or category. Therefore, let me add to this definition that analysis is an operation that, using a set of criteria, assembles objects from a given entity and collects their references. Once we are done with analysis, we should end up with a collection of references. and resolving such a reference should give us access to the analytical object and its properties and/or its type. To take the example of a cadence label, say PAC for perfect authentic cadence, then this label defines the object type, and the reference to the object would be the information where this object is located. The object itself may then point back to the actual music elements it represents. What follows is the second step of the dimensionality reduction, synthesis, which in this context can be viewed as an operation that arranges analytical objects in a given space in a way that expresses the relationships between them. The set of criteria that we had designed for the analytic step comes into play once more because it is encoded in the object's properties, which naturally play a role in how they will be arranged. Let's keep in mind that we can consider the outcome as a symbolic representation of a high-dimensional object, meaning that, vice versa, any symbolic representation can generally be thought of as the outcome of a dimensionality reduction. Since I have defined the two steps in computational terms, it is not very surprising that they have come out in a way that a computer could do them. And that is completely right. Probably most of you can think of situations where your analysis of a piece included some very tedious information processing that a computer could have done in a second while avoiding the errors that humans tend to make. I am not saying that we don't need human analysts. Humans will always be pivotal because it is them who want to analyze. It is the human who needs to invent a goal and the criteria for the analysis. And only humans know how to arrange objects in a way most suitable for other humans. However, I do want to advertise the possibility to let a computer do all the dirty work. But more importantly, the point I want to get across through the remainder of this presentation is that these definitions can help us comparing and thinking about different analytic approaches, techniques, and philosophies. In the next section, I will point out how the technique of annotation plays into the process of dimensionality reduction, to then proceed to the second part of the talk, where I give examples of how this technique changes when we move it from paper to screen. In the case of a mental entity, for example when doing a listening analysis, the analytic process is not very straightforward because it also happens mentally. It takes practice to strictly apply the criteria for assembling objects and for assigning properties and types to an ephemeral phenomenon. Also, it can be difficult to collect exact references because how do they actually resolve? That is why a listening analysis often synthesizes analytical objects into a list of symbols, for example timestamps and labels. The case is easier when we are already dealing with a symbolic representation, such as a score or the outcome of some previous dimensionality reduction. Because then we can use a very powerful technique which the media theorist Sibylle Krämer calls thinking on paper. Let's take the example of this annotated excerpt from Witold Lutosławski's 1968 piece Livre pour orchestre. The three colors seem to highlight different rhythmic layers. So with my definition we can say that the criterion for creating analytical objects was the rhythmic subdivision of any beat in any voice. Then the objects were assembled by encircling the notes and rests that the object references to, and a color code was used to assign an object type, expressing a particular property, namely a subdivision of 3, 5, or 8. So does that mean that annotation is the same as analysis? Well, I would say that annotation labels convey sometimes more, sometimes less information about the analytic operation itself. For example, The criterion used here was easy to reconstruct, but it is not explicitly stated. The same goes for the colors that allow for grouping objects of the same type, but there is no legend that clarifies the object properties. However, the labels are very explicit when it comes to referencing actual notes and rests. This is different for the chord annotations in this Robert Schumann song here. Of course, there's a bunch of conventions that help us to make sense of what these labels mean, but they are not very specific in what notes they actually reference. Also, the labels are not particularly consistent. They mix bass degrees, pure figured bass, and function symbols. In other words, the referenced analytical objects are not very well defined. They are less of an encoded analysis and more of a personal memory aid. Let's keep these things in mind when I proceed to the demo part of the talk, and I will start by quickly summarizing the handling of a virtual score as opposed to that of a paper score. When we open up the score, we can move it around like a paper score on a desk, zoom in and out, use keys to jump to particular places like beginning or end, or in MuseScore, use a convenient navigator that shows an overview of all staves and all measures. It lets us conveniently select, for example, this block of woodwinds, even if it spans over two systems. Of course, every notation software lets us switch to this continuous display of a score, which gives us an overview that is difficult to achieve with sheets of paper. Less experienced score readers enjoy the possibility to easily view transposed parts in concert pitch, and here we see how easily the transposed example is exported to a vector graphic for your next lesson or talk. Similarly, the tedious task of creating a partition for your next analysis paper is a matter of just a couple of clicks and keystrokes. For example, to get a quick grasp of what the strings are playing here, I select the bars to copy them, create a new document for my partition, insert the music, and use the implode tool to merge the staves together. Quickly hide the other staves, and voila. Needless to say that in a notation software we can listen to particular chords, easily change the notation to recompose, write into the score, and play around with our MIDI piano. So far so good, but how do you digitally annotate a score? As a quick example, let me bring up this short Schubert exercise in B major. MuseScore makes annotation very easy because it has a running cursor that we can use to skip from chord to chord to enter annotations. Compared to annotating a paper score, this has two major implications. Firstly, every label is attached to the metrical position in the score where you enter it, meaning that you can extract the labels with their positions, as I will demonstrate in a minute. And secondly, our labels naturally use the symbols available on the keyboard, which has the great advantage that later you can do basically anything with them, other than if they were, for example, snippets of handwriting. So here I show you the Python program that I use for storing my annotation labels as a table. It is called MS3 and is very easy to install and use. Here I use an interactive Python notebook to load the score, get an overview of annotations, and to save them to a file. In the leftmost column we see the measure numbers. The column named onset encodes the label's positions in the measure, and the columns staff and voice indicate to which layer the label is attached. For example, the Roman numerals are attached to the left-hand staff 2 and the others to the right-hand staff 1. By the way, MS3 also lets you delete the stored labels from the score or enter labels from a previously stored file. And now I come to a third and last major difference when annotating digitally. The knowledge that you can extract your labels as an annotation table leads to new ideas how to analyze and what kind of information you could encode in your labels. For example, at the DCML we use a standardized syntax for Roman numeral analysis, which MS3 recognizes and which it can split into their different components. In the exported table, we see for every label what key it is in. its different components such as the numeral or the inversion, and additional information such as the chord tone it includes, expressed as scale degrees. With the 1000 scores for which we already have such expanded annotation tables, we have already quite a harmonic database to search through, and we are looking forward to see more theorists jump on the boat and also create annotation tables, so that one day we can have a shared database of music analysis. Now we have reached the part where it becomes really exciting because of all the beautiful things you can do with such annotation tables, like combining the information about the keys of a sonata movement with its cadence labels, or like combining chord labels with the notes to which they are attached to look which composer actually used which notes in their minor tonic chords. But as we say in German, you should always stop at the nicest moment. If you're interested in what we're doing, feel free to check out our lab's homepage and GitHub, and I'll be happy to reply to your emails or talk to you on video. Thanks to the organizers and chairs for making this conference run smoothly. Thanks to the folks who are developing the free software tools I used for creating this video, and many thanks to you for listening and watching.